Welcome to Lesson 19, Computing Actual Areas from a Scale Drawing. Um, this will be the last lesson I will have you do in Module 1. Remember, as I had mentioned in class and via email, lessons 20, 21, and 22 are a project which is actually called an exercise in creating a scale drawing. So, the kids would create their own scale drawing of a dream classroom, is what the exercise is. Great, very worthwhile, but really demands a good number of classroom sessions to complete. So I won't do that now. I'm choosing to forge ahead into Module 2 instead after we finish our end of module assessment, which I am hoping you will do the last 2 days of this week. Okay, so that was just an aside. Now let's get back to Lesson 19, Computing Areas, Actual Areas from a Scale Drawing. And the first word I want you to pay attention to here is this idea of area. Okay, area. Now we've been talking a lot about sides. We've been looking at creating scale factors. If we had, let's say, if we had a shape, a couple of shapes, we would look at, maybe this is 4 units and this is 2 units. We would actually look at those sides and we might compare. So if this was the scale and this was actual, okay, we would put 4 over 2, so our scale factor would equal 2. Okay, now we are comparing sides, and this side, these lines right here move in one dimension. Okay, they are 1D in that sense. Okay, one dimension. Okay, whenever we measure a line is a good example of a one-dimensional figure. Area is different, and hopefully you all know this coming into this, doing this grade 7 math. This is something that's pretty critical, but I'm going to give a little fresh up here anyway, freshen up. Now when you calculate or you compute area, you are looking at 2D, or 2 dimensions, okay? When you calculate area, you are looking at measuring 2 dimensions. And we're going to see that coming up in the examples. But always remembering, and this is what's going to make a huge difference when we get to a part, the part of this lesson that may seem a little bit confusing to some. But just always remember, a line, a straight line, like the side of a rectangle, is a one-dimensional measurement. Okay, 4 units, the side is a one-dimensional figure, one-dimensional measurement. Okay, area, whereas if hopefully you remember, you are looking at both. You're looking at 2 different sides. Okay, so the area, well, in the case of something such as a square or a rectangle, you're looking at length times width, we usually say. So we have length here, width here, and what we do to those is we actually multiply those, okay? And then we get 8 what we call units squared, square units, and those units could be inches, they could be centimeters, they could be miles, whatever. Because in truth, what you're trying to find out with area, and again, I understand many of you know this already, is you're trying to find out how many square units of a certain size there are in the shape. Okay, in this case a rectangle, and you can see there are 1, 2, 3, 4, 5, 6, 7, 8 square units. Okay, and that's where we get that answer from right there. Okay, so anyway, that's just a short refresher on area. Okay, again, very, very important, but what's even more important is just remembering the difference between measuring a side and measuring the area of a garden, a wall, carpet, whatever figure you might be working with. Okay, now we are going to look at a series of examples, actually examples 1 through 3, exploring these area relationships. So the directions here are: use the diagrams below to find the scale factor and then the area of each figure. Okay, so we want to find two things. We're going to find the scale factor and we're going to find the area. Now with scale factor, we are just interested in comparing, okay, in comparing the scale drawing to the actual drawing, okay. So if we look at the scale drawing right here, and we take one of those sides, and that's 8 units. And if you remember, our whole k equals y over x equation, okay, always remember that this y is always, when you're talking about scale factor, is the scale drawing, okay. That scale drawing is that y. Okay, so in this case we would have 8, and then the comparable side on the actual picture is 4. Okay, and then we know 8 over 4 equals 2. Okay, so our scale factor is 2. And that would work the same if you looked at the other side, when you have 6 over 3. Okay, would equal 2 as well. Okay, so, alrighty, and now let's go ahead and look at the actual area. We're going to find the actual area of the scale drawing. Okay, actual area of the scale drawing is, remember we can, oh actually I'm sorry, we're not going to look at the actual area of the scale drawing, we're going to look at the actual area, okay, because it's the word actual. Okay, so I want the actual area, okay, not the scale drawing. Okay, actual area. And if we remember up top, my little refresher on area, you're trying to find out how many square units are inside of that box, in this case a rectangle. And remember, we just do the shortcut way, of course, is to do 3 times 4. 4 is your length, 3 is your width. Okay, and 3 times 4 would equal 12. Of course, we can see there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 square units inside of that rectangle. So our actual area is 12, and then in this case, square units. Okay, there's different ways to write 12 square units. Alright, but that's just one of them there. So the actual area is 12 square units. So we have that, we have our scale factor, okay, and now we're going to look at the scale drawing area, okay, and again, same way, we take our length, which is 8, times our width, which is 6, and we multiply those, and we get 48 square units. Okay, 48 square units. Alright, and again, if you were to count up all these, you would find out there are 48 little square units inside of that rectangle. Okay, trust me. Alrighty. Okay, so now we have some numbers. We have some numbers to work with. This next calculation is going to be new to us, probably all of us. Okay. The last thing we're trying to do here is we're trying to find the ratio of scale drawing area to actual area. Okay, now we have something that looks a little bit, it's going to look a little bit different. And actually there's a pattern, and after example 3, we'll talk about that pattern that you will see arise. Now, when we looked at this scale factor here, okay, we were, again, just to reiterate, to repeat, we were looking at sides. We were comparing sides. Okay, we just used the 8 and the 4. Okay, when we did that, right? The 8 here and the 4 here, and we could have done the same with the 6 and the 3. Just those comparable sides we were comparing, and that's how we did 8 over 4. Because again, when we're looking at a scale factor or we're looking at the constant of proportionality, we put the y over the x. Okay? So that was comparing sides. And again, remember that was what we call 1D or one-dimensional. Okay, one-dimensional comparison. Here, when we talk about square units, we are talking about 2D. Okay, so now we're talking about a 2D figure, two-dimensional figure, because it has both length and width to account for, whereas the line or the one side has only length. Okay, so ratio of scale drawing area to actual area, and what we would do then is just go ahead and put the scale drawing area, which is 48, okay, over the actual area, which is 12, okay? And again, the reason I did it 48 over 12 instead of 12 over 48 is for, well, a number of reasons. That's actually what we do when we're trying to figure out any kind of scale factor or ratio. But also it is it tells you right here, ratio of scale drawing. They give you that first. That's always going to be on the top. Okay, that's going to be your top or your numerator. Okay, to actual, which is going to be the bottom. Okay, the bottom number or the denominator. Okay, there you go. 48 over 12 is the same as 4. Okay, so the ratio of the scale drawing area to the actual area is 4. Okay, and you can see these are different. The scale factor, looking one-dimensionally, is 2. When you look two-dimensionally to find the ratio of scale drawing to actual drawing, you've got 4. Okay, so keep that in mind as we go to example 2. Okay, well here's example 2. Asks you to do the exact same things. Figure out your scale factor first, actual area, scale drawing area, and then the ratio of scale drawing area to actual area. So if you would pause right here and do that yourself with your parent teacher or whomever, and then come back and we'll do it together. Okay, so first for the scale factor, and hopefully some of you are getting so snappy and fast with all of this. Looking at comparable sides, and again we're looking one-dimensionally, so we have the actual at 9, scale at 3, and again remember the y over x, and that y is always the scale, so I'm going to put 3 over 9, which also equals 1 over 3. Okay, so that's my scale factor, is 1/3 or 1 over 3. And again, something that was mentioned in an earlier lesson, when you see that scale factor as being less than 1, which this is 1/3, you know that the scale drawing has got to be smaller than the actual. Whereas the example we had before, right here with the scale drawing, this was example 1. Remember the scale drawing was actually bigger, was larger than the actual drawing. So you notice that our scale factor was actually larger than 1. Okay, so keeping that in mind. Okay, now we're back here. We just figured out our scale factor, which is 1 over 3. Our actual area, which is over here, we have, go ahead and erase these. Okay, and again, I think many of you are getting snappy. You've got this done, and if you have this done and you don't need to watch this, just move on ahead, huh? So we have 9 times 6 for actual, and that is going to be 54 units squared. Here's another way to write square units. And again, we don't often use units. We just use units because we don't want to commit to centimeters or inches because they're just examples, okay? So 54 units squared, okay? Scale drawing, 3 times 2, 6 units squared. And now we look here, we look at ratio of scale drawing, okay, area, which is 6 over actual area, which was 54. If we reduce that fraction, again, this needs to be something that is done automatically. I see a relationship between 6 and 54. They're both divisible by 6, and I know 6 divided by 6 is 1, 54 divided by 6 is 9. And here you go, 1/9. Okay, so now we have the ratio of the areas as 1/9, and the scale factor of the one-dimensional sides as 1/3. So again, good to take a look at these two and how they compare. Here's our 2D ratio. Here's our 1D scale factor. Let's go back real quick and take a peek over here. If you remember, our 1D scale factor here was 2. Our 2D ratio of area was 4. Starting to get any kind of suspicion as to what's going on? All right, well, let's go ahead and look at example 3. Okay, we'll scale, example 3, looking a little bit different to you, of course, because example 3 presents us with 2 triangles to compare, okay? And hopefully many of you understand or remember the equation for the area of a triangle. Okay, and we could indeed count all of this up, but it's pretty difficult because we've got little bits and pieces. You can see somewhere here we got half a unit, half a square unit there is circled. We got a little piece here missing. Okay, so not so easy to do that. Instead, you can write this down somewhere if you've forgotten it, and it just all makes sense. The area of a triangle, okay, area of a triangle equals 1/2 length times width or height or whatever, okay? Because you're going to take this and this measure, these two one-dimensional measures, one dimension, another one-dimensional, and we're going to multiply those, but that would actually give you the area of a rectangle that big. But if you notice, what you've done here is you've kind of, with this right here, you've added a whole half. So you can see how this triangle down here, okay, is just half of a larger rectangle. Okay, it is just 1/2 of this large rectangle. Right? So when you multiply 12 by 8, you are doing the exact same thing you did over here, where we did 6 times 9. We got the area of this entire rectangle. Okay. Now when we do 12 times 8, we again get the area of this whole rectangle, but that's not what we're interested in. We are interested in only in this part here, okay, which is half of it. Okay, this is just, probably get, this would be just 1/2 of the whole thing. Okay, so if we do 12 times 8, we get 96, And then if we cut that 96 in half, or just divide by 2, we get 38 units squared. Okay? I know we haven't gotten there yet, but just in case you had forgotten how to go about or how to think about the area of a triangle, and hopefully that makes sense to you. Okay, so knowing that, you can go ahead and pause and try it on your own, and then come back when you're ready. Okay, we're back, and hopefully you had some success with this one. Okay, so let's go ahead and let's do scale factor first. Okay, sticking with our one-dimensional scale factor, and again, just taking two corresponding sides, which we would do this one here 8, and this one here 6. Okay, the 8 is our scale, so that's going to go on top. Okay, so it's going to be 8 over 6. Okay, which can be reduced to 4 over 3. Now, hopefully, this is becoming more and more. I hope this is becoming more and more quick for you to do. Okay, more and more natural, just right away knowing how to reduce fractions. Okay. All right, so let's go ahead and do the actual area. Here's our actual picture over here, and using the formula that you may have known already, or hopefully you learned when I just told you a few minutes ago. Let's go ahead and look at actual. 9 times 6, okay, 9 times 6 is 54, and then if we take 54 and cut that in half, we will get 37, but 27, okay, 27 units squared. And again, remember, really try to emphasize this with kids a lot, is that you want to always, you have to make note of the fact that we are talking about square units here. That is so important, because 27 is not a correct answer. The actual area is saying it's 27 units. That's not correct. You know why? Because 27 units is just a one-dimensional measure. Just like this right here, 8 units would be a one-dimensional measure. But when I say units squared, I know we're talking 2 dimensions. Okay? Scale drawing area, we do this same process. We actually did this already. 12 times 8 was 96. And then we got half of 96, which we came up with. I think I might have said the wrong answer before. Did I say 38? Well, anyway, that's 48 units squared. Okay? Units squared. Boy, I'm sorry if I said, hold on one second, I want to go back to that one. Did I? Oh, I didn't. Oh, I didn't keep it. Anyway, yeah, I think I might have said 38. Excuse me for that. But anyway, yeah, 48 units squared. Okay. All right, and then we're going to do again the ratio of scale drawing area to actual area. And again, we're going to put that, of course, we're putting 48 over 27. Okay, and again, hopefully people will know, they see a number that's related. This one might not be as easy to see, but using divisibility rules, for example, could help you. But eventually, hopefully, many of you got to the fact that 3, both of these is divisible by 3, and therefore the answer here would be 16 over 9. Okay, 16 ninths. All right, that is the now the ratio scale drawing area to actual area, which is our 2D ratio, and here is our 1D. Just D is for dimension. 1D scale factor. Okay, how do these two compare? Okay, well, now we've got all these different comparisons to make. We've got 4/3 and 16 ninths, and then we have 1/3 and 1/9, and then we have 2 and 4. Okay, so let's investigate further. Okay, you may have answered these questions already by yourself, but I'm going to go ahead and do this with you so we could again talk more about it. And if this is something that is seems very, very difficult to you, I don't want you to stress over it. It is a very interesting relationship, and a relationship that makes a lot of sense, but I don't want you to stress if you don't quite get it. Okay? Because some of these concepts will come up again. All right? So here we go. When the scale factor of the sides was 2, then the ratio of the area was, and you can go back and look, or it might be right there in front of you. Okay, but that ratio of the area was 4, if you remember. Okay. When the scale factor of the sides, again, look at this, scale factor of sides. See that? 1 dimension. And then the ratio of the area, okay, 2 dimensions. All right, 1D, 2D. Okay, so now when the scale factor of the sides was 1/3, then the ratio of the area, if you remember, was 1/9. Okay, when the scale factor of the sides was 4/3, then the ratio of the area was 16/9. Okay, so now if you haven't done this yet, I want you to think about this this question and go ahead and jot some thoughts that you may have. So based on these observations, what conclusion can you draw about scale, factor, and area? So this is what we want right here. I want to ask you, what conclusion can you or we draw about scale, factor, and area? How do these two, scale factor and area, or actually ratio of the area, okay, ratio, okay, how do they compare? Okay, all right, so go ahead and pause and discuss it. Look those numbers over again. 2, 4, 1/3, 1/9, 4/3, 16/9, and see what you think. Okay, so hopefully you had some observations. Again, I'm not sure. I'm not sure. It depends on probably on your your sophistication with math and with different concepts as to whether you saw this relationship or not. It's okay. But whatever you did is fine. All right. But I'd like you to take a look at this as I show you. The truth of the matter is, when you look at scale factor, for example, let's take 2 in this one right here, all right, and then you have the 4 as the ratio of the area, we can compare those. And some of you might have said multiplied by 2, okay, so you can put, we multiplied, the relationship might be multiply, scale factor by 2 to get area ratio. Okay, I'm just abbreviating here. Okay, so you could have said that, multiply, thank you. You could have said getting from here to here, from scale factor to area ratio. You could have multiplied scale factor by 2 to get AR. Okay, now let's check that relationship. So how about 1/3 and then 1/9? Okay, and all these have to have the same exact relationship. Okay, so let's test this from 1/3 to 1/9. Can we multiply scale factor by 2 to get the area ratio? Let's go ahead and try that over here. 1/3 times 2. And remember, with multiplication, you're just doing straight up multiplication there. So 2 over 1 just makes it a little bit easier to look at. So 1 to 2, 1 times 2 is 2, 3 times 1 is 3, and we have 2/3. So when we multiply 1/3 times 2, we get 2/3. We don't get 1/9. Okay? So that doesn't work. And maybe some of you thought that, and that's pretty natural to think because you see it work once, just go with it. Okay? So that is not our relationship. So therefore, think to yourself, what is another way that the 2 here is related to the 4? How would you get from 2 to 4? Okay? We multiplied by 2, it worked, but then it didn't work for the next one. What's another thing you could do to 2 to get 4? And hopefully, since we've been talking about square units this entire time, maybe some of you thought, hey, I can square the scale factor to get area ratio. Okay, and if you did that, 2 squared equals 4. And it does work for 2. Okay, and most of us know that. If you don't know that, it'll come up again. It'll come up again in our discussion of rational numbers coming up real quickly. So, yes, 2 squared equals 4. Okay, and again, what it means to square a number is to do what? Is to multiply it by itself. Okay, so squaring a number. If I square 2, I do 2 times 2, and I get 4. Okay, if I square, let's get rid of that. If I square 3, I do 3. 3 times 3 equals 9. Okay, and that's what 3 squared. Okay, 3 squared and 3 times 3, it's the same thing. Okay, just to remind you, or maybe give that to you, those of you who may have forgotten it or may have never learned it. I just hope that's not the case. Anyway, here we go. Okay, so now let's go ahead and square 1/3. And how do you square 1/3? 1/3 times 1/3 equals 1 times 1 is 1. 3 times 3 is 9. Look at that. Yes, indeed, it has worked. Okay, but again, like we found out before, when it works one time, it worked here, well, even when it multiplied by 2, but then it didn't work with 1/3 to 1/9, but now it works for both. We always still have to check. So let's just check the last one. I'll check this one right here. Okay, so its scale factor was 4/3. Okay, the ratio of the area was 16/9. Okay, let's check it. If we're going to check it, we're going to do 4/3. I usually write 4/3 squared like that. Okay, whenever you're squaring a fraction, you want to put the fraction in parentheses. Okay, but that equals, of course, 4/3 times 4/3, which equals 4 times 4 equals 16. And guess what? 3 times 3 equals 9. And here we go. We have our relationship. We have uncovered the relationship between scale factor and area. When you calculate your one-dimensional square factor, for example over here, 2, the square of that number, when you square that number, you come up with the area ratio of 4. Okay? So that, to me, is very exciting. I hope is as exciting for you. If you didn't understand it or need some more help, watch the video again or give me a call. I'll send you a personal short video to help you out. Okay, so one last question that that I skipped there is this last one here. If the scale factor, I'm reading right here, if the scale factor of the sides is R, then the ratio of area will be, okay, so if you could think about that for a little bit. You can pause here. I'm just going to pause and not say anything for a couple seconds, but pause and then come back. Okay, we're back. Yes, so if the scale area, so what they're saying here, so they're saying, so R, again, using a variable, using an unknown, any number at all, plug in anything to this, okay? If the scale factor of the sides is R, and that R, of course, stands for scale factor here. Okay, because these numbers, I mean, these letters, they'll stand for something. Scale factor equals R squared. Okay, R squared, and this is our area ratio. Okay, so therefore, with this equation in mind, we could always plug in anything. So if we find out that the scale factor for a certain excuse me, scale drawing is 9, for example, we know R equals 9. We can plug that in, and if R equals R squared, that means 9 equals 9 squared, which equals R equals hold on a second. Sorry, it was a little bit confusing here. I didn't mean to write R equals R squared because that's not true. Equals R squared. This is scale factor, and then this is the ratio of the area. Okay, and one doesn't equal the other. They're two different things. Okay, so all right. Anyway, so but if we know R, that's the idea. If we know R is 9, then we know that the ratio of the area is going to be R squared. So 9 squared equals 81. So this will be our ratio here. Okay, that'll be the ratio of the area, okay, between a scale drawing and an actual drawing. Okay, and in this next example, this is going to take a bit of work, and going to try to make our way through it slowly and steadily. Again, some of you will get this quickly. Some, may end this lesson not truly understanding how to do it, but that's okay. Just with continual practice, we will get this eventually. Okay. So here we go. The first part I think you'll be able to do, all of you. So here we go. They said yes is example 4. The student government liked your half-court basketball plan. They have asked you to calculate the actual area of the court so that they can estimate the cost of the project. Based on your drawing below, what is the area of the planned half-court going to be? Okay, and if you remember, this is the exact same plan here. I'm going to move this so it'll be easier to see in a minute, but we had some numbers from yesterday in class, on Monday on class. Again, same scale, 1 inch equals 15 feet, 1 inch on the scale drawing equals, corresponds to 15 feet of actual length. Okay, and we figured that we had this here was 25 feet, and then we had 30 feet going across this way based on our scale. Those are the numbers we got yesterday. Okay, so here they are again. So 25 feet by 30 feet, and again, to find the area, we are multiplying, okay, because we're multiplying these two dimensions, the one dimension that moves that way and one dimension that moves this way, width by length. And then if we went ahead and multiplied 25 by 30, hopefully you know that would equal 750 square feet. Okay, so our area of this basketball court is 750 square feet. Okay, Now we're going to be asked another question. Okay, so now I'm going to read this question here, and I want you to just pause and take a moment to do whatever calculations you need to do, because you will need to do some calculations to figure this out. If you have no idea whatsoever how to start this, just don't pause at all. But I'd like you to be able to pause and maybe at least talk to your parent teacher or someone else about it. Okay, and here it is. It says, does the actual area you found reflect the results we found from examples 1 to 3? Okay, so we know that the actual area here is 750 square feet. Okay. Now examples 1 to 3, those are the ones that we did beforehand. I can't scroll back to those right now because it seems like I've lost them. But those were the examples where we found the scale factor, and then we compared it to the ratio of the areas, okay, in each 1, 2, and 3, all three of those examples, and we found a relationship between the scale factor and the ratio of the areas, and we found out that to get the ratio of the areas, we took the scale factor and we squared it. Okay, so we're trying to find out if that relationship is reflected in this example as well. So you're going to need these numbers that go along with this problem. Go ahead and check it out, and pause and come back. Okay, in order to decide whether the results we found here reflect the results we found in the examples 1 to 3 we did previously in this lesson, we need to gather some data. So first of all, let's look at the area. Well, we could look at scale factor first, since we've been doing that usually first. So scale factor, again, which compares the scale drawing, okay, and the actual. All right, so we realized that that was right here. That's our scale factor right there. Remember, we had for every 1 inch on the drawing, there was 15 feet in the actual. Now we also talked about, now in this case we're using the ratio. We're actually comparing 1 inch to 15 feet. We had also talked about in class, we could do it that way, but it gets a bit tedious because there are lots of conversions to perform. But in this case we have 1 inch to 15. So again, we'll just apply a scale factor of 1 to 15. Okay, that's our scale factor. That's our excuse me, our first bit of information we need. And now the area ratio. I mean, it's a ratio between the scale drawing, and the actual. Okay, so when we go ahead and do the area of the scale drawing, we have 1 2/3 inches and 2 inches. So we need to multiply those. So again, hopefully we're understanding how to do this. Whenever I multiply fractions, I always want to make both fractions and make them both improper fractions. Okay, and this would be 5/3. Okay, and you can see that one whole is 3/3 plus another 2/3 is 5/3. That's how I change this mixed number here to my improper fraction. Okay, so then if you do this multiplication, 10 over 3, 10/3. Okay, so the drawing has an area ratio here, has the area, actually an area of sorry, not area ratio, but an area of 10 over 3 inches squared. Okay, and again, we're not as interested right now in the inches squared as we are the actual number, which is 10 over 3 here. Okay, that's the area. 10 over 3 inches squared is the area of the drawing. We should probably actually just take area ratio out of there, because we're actually finding area right now. Okay, the ratio down here, this is our ratio right over here. Okay, so you can maybe pause this and write this down if you want to somewhere on some notes, because I'm going to go ahead and erase it. Okay, give you a little time there to pause. but now I'm going to erase it. All right, that's how I figured out the area of the scale drawing. Now to get the area of the actual, I just apply these numbers right here at 30 feet, 25 feet, multiply those, and I get 750 square feet. Okay. All right, so that's 750 feet squared. And again, not as interested in the in the fact that it's feet squared. I'm just interested mainly in this number. Okay, 750. So next step is to find the actual ratio, the area ratio, right down here, of the this would be, it's actually more correctly called the area ratio. That compares the drawing area to the actual area. So that would look like this: 10 over 3 over 750, and this looks familiar. This is a complex fraction again. Okay, when either one or more of the numerator or the denominator is a fraction. And we did this some time back, and we did quite a few of them. I hope you learning to love them. I know some are have some difficulty with this idea, but let's go ahead and practice this again. Okay, so I'm going to go ahead and get just a whiteboard up here. Give myself some more room, and we're going to go ahead and erase some of this stuff here. Okay, what I need though is I just need to remember that I have scale factor of 1 over 15 and 10/3 over 750. Okay. Okay, so erase that. Sorry it takes so much time there. But here we go, scale factor. And I don't need to do anything else with this because I've got this down. Okay, but now I want to work on my my area ratio. Okay, so that was, remember, 10/3 was 10/3 square inches was the scale drawing, and then we had 750 square feet was the actual area. Okay, so we're going to go ahead and divide these. Okay, and you remember numerator comes out, but then denominator, if you remember, we take that denominator and we flip it over. So then we're going to have 1 over 750. Okay? All right, so 1 over 750. That's how we do this division. Remember when we divide fractions, okay, or just divide fractions by a whole number, whatever, we flip over, this would be flip over this denominator here. Okay, when we divide, we always a second one, the second fraction that we are dividing into the first fraction, or the divisor. Okay? All right, and then again, our cross cancellation to make our life easier. Cross out the 10, because they're both multiples of 10. And that becomes 1, and that becomes 75, which is really brilliantly easy. And then 1 times 1 equals 1. And then 3 times 75 equals 225. Okay, so this is now our area ratio. Okay. All right. Now I'm gonna just go ahead and actually, why don't I put that up here, and then we can work down the bottom. Equals 1 over 225. Okay. And these are the two numbers we compare, and hopefully you remember how we decide, or how we can figure out whether these work the same way as in examples 1 through 3. Because if you remember, let's just go back and just remember again. I can't go back. I've lost those slides. Well, not lost them, but not easy to get to. But anyway, you remember when we had a scale factor that one time of 1/3, or actually let's do the one that came before it, which is a lot easier, huh? We had a scale factor of 2, and then we had an area ratio of 4. Remember? We decided after looking at other examples where we had a scale factor of 1/3 and an area ratio of 1/9, okay, we know that to the relationship between scale factor and area ratio is you take your scale factor and you square it, and that gives you your area ratio. Okay? All right? So it worked out for those two as well as the third example. Let's see if it works out for this example right here. And some of you may know that whether it does or does not. Okay. So if this were true, that would mean that 1/15 or 1/15 squared has to equal 1/225. Okay? So how do we figure this out? Well, of course, when you square a number, you multiply it by itself. So 1/15 times 1/15, and I don't care if you don't know this or you use a calculator. Okay? 1 times 1 is 1. And yes, indeed, if you multiply 15 times 15, you get 225. So, yes, this relationship does indeed hold. Our basketball court relationship is similar to the others in that scale factor squared equals the area ratio. Okay? Okay, I'm going to have you pause in a second here, pause in a minute, and do these exercises. So there are, let's see, 1, 2, 1, 2. There's two different problems, two different exercises with multiple parts to them. So I'd like you to pause, take about 15 minutes to complete those, and then I will come back and I'll just give you the answers. I won't go into too much of an explanation. I do not want this video to run too far over an hour. We're not at an hour quite yet, but I do want to close the lesson before I let you go and complete your problem set and an exit ticket. So go ahead and take some time to finish these. Do as many as you would like, then come back and you can get the answers. Okay, this first exercise here, the triangle depicted by the drawing has an actual area, and this was really important to pay attention to, an actual area of 36 square units. What is the scale of the drawing? Note, each square on grid has a length of 1 unit. Okay, now you may or may not have realized that this actual area, what they're saying is that there's another triangle that exists somewhere, and it's the actual area of a triangle. It's the actual triangle. Okay, so this one over here, they're saying that it has an area of 36 square units, which would probably make it doesn't really, it could be many things, but anyway, this is 36 square units. Okay, so we know that that's over there. Now if you look at this one here, you can see that it is actually a 3 by 6 dimensions here, and if we do that, we do 3 times 6, that equals 18. But we know, of course, that we are only looking at half of that rectangle that the 3 by 6 would build. Okay, and then if we just multiply that by a half or divide by 2, we get 9. So this one here, this is our scale drawing. Okay, this is the drawing scale. Okay, this is the scale drawing, and it is actually 9 units squared. Okay, so now if we look to compare this, the area of the scale to the area of the actual, you remember when we did that, we would do, remember, the actual, the scale over the actual, which was 9 over 36, or 9/36. Okay, we could then see that this would equal 1 over 4. Now, based on what we learned beforehand, this, the area ratio is r, remember r squared, or was the scale factor squared, okay? So this was the scale factor squared. So we're going to say that we need to know what r squared equals 1/4. So what number or what fraction here will give us 1/4? And again, it's something that we need to know and need to be ready to calculate on a whim. But that would be actually, trying to get some room here. How about over, oh darn, hold on. I'm going to get rid of all this. Okay. So, if r squared equaled 1/4, then that means r equals 1/2. Because 1/2 times 1/2 equals 1/4. Okay? So r, which is our scale factor, is 1/2. As you can see, or as you might realize, I'm not going to go through this suburban apartment, city apartment problem or exercise because of the difficulty in measuring. I'm sorry I didn't warn you ahead of time. We talked about how these, how when they reproduce, they don't reproduce very well or to scale. So I have skipped these. Hopefully you saw my little note that I put ahead. So, okay, so we're just going to go ahead and close now. Okay, so in closing, here was our lesson summary. If we are given the scale factor, and in this case, in this lesson, they've been talking about scale factor as being r, and it represents the relationship between scale drawing length and actual length. Okay, and again, these are one-dimensional measurements. Okay. All right. The square of this scale factor, this is R2, okay, because that's the square of it, represents the relationship between scale drawing area and actual area. Okay, and again, area is a two-dimensional measure. Okay, and it would make sense that this two-dimensional measure would be squared. Okay, because that's how you calculate area, is by squaring. Okay, you're looking at square units always. So for example, if 1 inch on the scale drawing represents 4 inches of actual length, then the scale factor r is 1/4. Okay, on this same drawing, 1 square inch of scale drawing area would represent 16 square inches of actual area, since r squared is 1/16 right here. Okay, and the way you get that is by taking r and squaring it, which of course means multiplying it by itself. Okay, which equals 1/16. Okay. Alrighty. Again, I know this is not as easy on some as it is on the others. But please, if you have some difficulty with it, if you have some time, go back over it again. If not, we're just going to forge ahead. What I want you to do now, again, is to just go ahead and feel free to skip 20, 21, 22. I will not post lessons for them. And just go ahead and take some time to catch up and finish your, do the end of module assessment. I'd like you to use all the tools at your disposal to complete that assessment, and then we will correct that in class on Monday. Okay, good luck.